Hello, welcome to Prajim Technologies. I am Venkat. This is part 5 of Dotnet Basics. In this session, we'll understand how the Dotnet runtime environment finds the assemblies that it requires during program execution. To understand this better, we'll actually look at an example. I have a simple console application here. To this console application solution, I'm going to add another project. Let's add a class library project. Okay, Visual C# programming language class library, and let's call this class library. Click OK. So we have a class library project, and within this class library project I'm going to have a very simple class called sample, and as part of this class let's have a simple static method that returns a string, and let's say maybe get message is the name of the function, and all this does is returns a string. Alright, so we have a very simple class library project here. Okay, now if we want to use this class library project within this console application, obviously we have to refer to that assembly. So let's build this solution so that we have the assembly generated. Now go into the references folder, right click, add a reference, and we're going to dig through class library project, bin and debug folder. We select the class library assembly. So we told the console application we are going to use this class library, so we go into the console application class and we use the using directive using class library. And we know that within this class library assembly we have got a sample class within which we have get message static method which returns a string. And now if we run this, as you might expect, it's going to print that string onto the console. Alright, now let's see. If you look at this program, this console application, it's actually making use of this class library assembly. And that's our custom assembly which we have created. Now let us see, when we execute this project, how does the .NET Runtime environment finds the, in this case, the class library assembly that it requires. So now when we added the reference, as you might have expected, what would have happened is it would have copied this class library project's assembly into the bin folder of this particular project. So if I go ahead and open this folder in Windows Explorer, if we get into the bin and debug directory, you should see a class library project, assembly, and then the console application assembly itself. So when we run this, we should be able to execute. Now, for this application to be, to properly execute, all we need is two files. One is this executable, and we know this executable is the console applications assembly, and this depends on this class library assembly, because we are making use of the sample class which is present in this class library assembly. So we need that assembly as well. And apart from that, this program also requires the system assembly from .NET Framework. Because the console class is present within the system assembly. We'll not worry about that piece at the moment. All we are worried is, if you have understood until now, for the console application to execute, it requires this executable and this assembly. So let's just extract those two. Let's just copy them and put them into a specific folder. So let's say I have C drive and my application. And let's copy paste those two assemblies here. And now all you need for this console application to run is these two assemblies. So when I execute this, it works out without any problem. Now let's do one thing. Let's delete this assembly from here. I'm going to delete that. Instead of deleting it, I'm going to cut that and maybe create another folder, or just paste it in the C drive for the time being. So if you go to my application here, you only have the assembly. You don't have the the dependent assembly, the class library assembly. So when I execute this at runtime, CLR checks this assembly's manifest. Let's see what happens when we execute this. So when we execute this, as you might have expected, look at this. system.io.file not found exception. Okay, so it's not able to load this class library assembly. Okay, if you remember, what we have done is we have just moved that assembly from this folder onto another into another folder. Okay, so how does what is the search logic behind the runtime environment trying to find this assembly? It's very simple actually. If you look at the presentation here, all it does is, first of all, .NET figures out what version is needed. Okay, in this case, what has actually happened is, okay, let's close this first. Okay, so when we execute this program, what happens is the .NET runtime environment checks the manifest of this assembly. Okay, and in the manifest, if you don't know about what an assembly's manifest is, please check the previous tutorials in this video series. We have already discussed about that in a great detail. So what happens at runtime, the CLR basically checks this assembly's manifest, which contains the information about all the other dependent assemblies. Like what's the, for example, in this case, this console application depends on class library assembly. Okay, so it checks that in this assembly's manifest, okay, which version is required. And then what it does, if the dependent assembly is a strongly named assembly, look at this. So .NET figures out what version is needed. Usually this information is the information about the dependent assemblies is present in the application's assembly manifest. CLR checks that, as well as it also checks the configuration files. Every application, in this example, we didn't use the application configuration file. For example, here we have app.config. This is nothing but the configuration file. Okay, every application usually has that, irrespective of the type of the application. Because ours is such a simple application, we don't have any configuration specified. That's why we didn't use that. But in reality, we do use configuration files. And there are several configuration files, like application config file. Within the subdirectories, you can have more configuration files, which will effectively override this configuration file. Similarly, at the machine level, we have a machine.config file. That's another configuration file for all the .NET assemblies that execute on this machine. So there are several layers of these configuration files that can be present. In addition to these configuration files, you can also have policy files. Okay, so what .NET Runtime environment basically does is it basically checks the assembly manifest. It also checks the configuration files if there is any overridden information. For example, in the assembly's manifest, it might be version 1.0, but in your configuration file, you can override that. Okay, instead of loading 1.0 assembly, load this assembly. You can override that information using any of these configuration files. So .NET Runtime environment checks these configuration files as well for any overridden information. And then, if it is a strongly named assembly, it searches the GAC. But in our case, if you look at this assembly, class library assembly, we did not sign that with a private or public key pair. So obviously it is not a strongly named assembly, it's a weak named assembly. So if it's a weak named assembly, .NET doesn't search the GAC, because we know that you cannot install a weak named assembly into the GAC. Okay, that's why it doesn't care to search for class library assembly in the GAC. Okay, then what it does, it checks. Okay, so this is a weak named assembly and there is no overridden information in the configuration file. Okay, and it doesn't check the GAC. So what it does now at this point is, if the assembly is not found in the GAC, obviously it doesn't even care in this case because it's a weak named assembly. And if there is a config file, in the config file you can actually specify, okay, instead of searching in this location, go to this location, search for the assembly at this location. You can specify that in the config file. So if there is a config file and if you specify the location there, it searches. The .NET Runtime environment searches that location. But in our case, we don't have a config file at all. I mean, there is a config file, but we didn't specify any information. And if, as a matter of fact, we moved the console applications assembly and the class library assembly into this folder, so there are no other files. So obviously in our case, we are not making use of configuration file to specify another directory to search. So what's going to happen at that point, it will then search the directory where the executable is present. In our case, it looks in this assembly and it didn't find that here as well. So At this point, it searched all the possible locations for the dependent assemblies. It didn't find that. Finally, what's going to happen, the application will terminate with an error. And that's what has happened. Because if you look at this, in this folder, it didn't find that assembly and it terminated with an error. Okay, but then in reality, this is what is the .NET assembly resolution algorithm that is usually used. Okay, all right. So if I move the assembly back into this folder from C drive, it should work. So I have this assembly here, class library. So if I take that and if I move into again this folder and then try to execute this, what happens? It finds that assembly within the folder where we have the executable and it executes that. Okay, another important thing to keep in mind is that version checking is not done for weakly named assemblies. Now this is very interesting and important to keep in mind. Let me show you that with an example. Let's open Visual Studio command prompt so that we can use the ILDASM tool. So let's run that as an administrator and then let's invoke ILDASM. Okay, so we have this ILDASM tool. Let's open this console applications executable with this ILDASM, and it's present in my application. Open that. So if you look at the manifest of the executable, in the manifest you should see that, okay, this executable is dependent on class library assembly version 1.0.0.0. Okay, now what's going to happen if I change this version of the assembly to 2.0? Is that going to make any difference? Absolutely no. Because why? For weak named assemblies, it doesn't really care about the version numbers, and that's why these assemblies can cause DLL hell as well. Okay, so if I have downloaded a program from the internet, for example, and when I downloaded that program, let's say accidentally that program had class library as the name of that assembly, it would have overridden this assembly, and maybe the methods within that assembly would have been changed, and this specific executable looks for that specific methods within that assembly. It will not find them, and then you have the application crash, and this is what is termed as DLL hell. However, we'll talk about DLL hell in a great detail in the next session with an example, but right now let's understand this. Okay, and if you open this class library assembly with the ILDASM tool, so let's open the class library assembly, and if you look at this class library assembly, it's version 1.0. So your executable needs version 1.0 of class library, and you have that within this folder, so it executed. Now instead of assembly version 1.0, if I have version 2.0, will my application run? It will happily run. Why? Because version checking is not done for weak named assemblies, and if you remember, we did not sign this class library assembly with a private public key pair, so it's still weakly named. Let's look at that practically. Now let me go ahead and change the version number of the class library file from 1.0 to 2.0. So I'm changing that to 2.0. Let's build this project. So I'm building that. Let's open that folder in Windows Explorer, go into the bin, debug, copy that, and move that to my application folder. Paste it. It will ask you to copy and replace, and I'm going to do that. And now when I run, okay, we have this open, so we need to close that. Okay, let's paste it again, copy and replace that. So it's copied and replaced. Now if I run my console application, look at this, it's happily running. And if you check the version of class library now, it should be 2.0. So let's open ILDASM. So if I open class library, and if you look at the version is 2.0. But if you open the executable manifest tells you it requires class library assembly of version 1.0, but this version is 2.0. in spite of that, my console application is still running without any issues. And the reason is very simple. For weak named assemblies, the runtime environment doesn't care about the version number. As long as the assembly is there, and as long as the methods that your console application is dependent upon are there with the same name and same return types, your application is going to run without any issues. But on the other hand, if your class library assembly was strongly named assembly, then all this would have failed. Let's look at that example now. Let's make the class library assembly strongly named, and then we will see how it works for strong named assemblies. Okay, let's go ahead and delete this assemblies. Alright, so if we want to convert this assembly into a strongly named assembly, all you have to do is sign this assembly with a private public key pair. And if you remember, we can use the strong naming tool to do that. And using that tool, we have already generated a key pair in our previous sessions, which is present in our C drive. So let's copy that. And if you're not sure how to do this, please check our previous videos. Alright, and we use the assembly key file attribute, and to the constructor of this we pass in the name of the assembly key file. Since it is present in C drive, C:\\/ to escape the backslash. And now let's do this. Let's get rid of this reference, and let's change this version for 1.0. So we are strongly naming this assembly, and we are changing the version to 1.0. Since we have removed the assembly reference, we need to comment this, otherwise our application will not compile. So let's rebuild the solution. Okay, now what happened? We strongly named this class library assembly. Okay, so now let's go ahead and add a reference to that strong named assembly. So add a reference to that class library assembly. So this is strongly named, and we added a reference to that assembly. Now we can uncomment this, and when we run this, it should work as before without any issues. The only difference now is that we strongly named class library assembly. Okay, now let's open the Introduction to C# console project. Open that in Windows Explorer, go into the bin, debug, and take these two assemblies and let's put them in my application folder. And now if I execute, it should work without any issues. Now if you quickly look at class library assembly and console application at this point using ILDASM, so if we open the class library assembly, and if you look at that, class library assembly is version 1.0. Okay, and we have the manifest of class library assembly itself. Now let's go ahead and open the console application. So when I open the console applications assembly, and if we look at the manifest right now, look at this. It is now, this console application is now dependent on this class library assembly whose public key token is this one and whose version is 1.0.0. Now for some reason, instead of version, now this assembly, this class library assembly is a strongly named assembly. Instead of version 1.0, if somebody puts version 2.0 in here, it wouldn't work now, because if it's strongly named, the runtime environment does check for correct version match. If there is a version mismatch, it will not bind that assembly to this executable and immediately throws an exception. Let's see how to do that. Okay, let me change the version of the class library assembly from maybe 1.0 to 2.0. Okay, now let's close this ILDASM. Let's go to my application, execute this. It works now. But if we change the assembly version to 2.0, build the class library project, get into the bin folder of that project, copy that assembly, and move that to my application, see what's going to happen. So I copy that, move that into my application folder. Let's copy and replace that. Now let's execute that. And before that, let's see. Let's open ILDASM once again. Look at the console application, and if you look at the manifest, it requires class library assembly version 1.0, and this is the public key token. It starts with 58. Now let's look at class library assembly. If you look at class library assembly, it's version 2.0, but our console application requires 1.0. But if you look at the class library assembly itself, it has got the methods with exact the same signature we need. Okay, but however, now if I try to run this application, it's gonna fail. Okay, so let's execute this. Look at this. You got that file load exception. Could not load file or assembly class library version 1.0. Why? Because here we have version 2.0, and we didn't have this problem when the class library was not strongly named. Because why? The .NET runtime environment doesn't care to check the versions, whether versions will match if they are not strongly named. But if they are strongly named, it does care about it, and that's why we have this error. Alright, so since this is strongly named, it has to be version 1.0. So on the other hand, if I come back, change that to version 1.0 and then build the solution and put it back into that folder, it should work as before. So build that, open folder in Windows Explorer, get into the bin, debug, take that and move into my application folder. It should work now. So copy it, copy and replace, execute this, it should work. Now we know that the resolution algorithm is very simple. .NET figures out what version is needed. In this case, it figured out that okay, it requires .NET version, class library version 1.0, and then we didn't override that information in any of the applications or machine configuration files. So what it does, it searches CAC because it's a strongly named assembly, so it searches CAC. Obviously we didn't put this class library assembly in the CAC, so it wouldn't find it there, and then it comes back, okay, it didn't find it in the CAC. So what it does, okay, it checks, okay, is there an application configuration file, and is there any other configuration there to find the assemblies, and obviously we don't have that. Then what it will do finally, it will check the application folder which contains the executable, it finds it there and then successfully executed. On the other hand, if you move it from here to anywhere else, then the program will crash. Okay, now since this is a strongly named assembly, if you think this this assembly is going to be reused by multiple applications running on this machine, it is safe to move it into the GAC. When you move it into the GAC, then it need not be present in this folder. Let's do that actually. Let's try to install that into the GAC. And obviously to install that into the GAC, we can make use of GAC utility. So cd /, and let's go to my application folder. So cd my application, and here we can use the GAC util tool -i, and we can use this is the name of the tool assembly. So copy it and paste that. So the moment we do that, what's going to happen, this assembly is now going to be installed into the GAC. Now if I delete that from here and if I execute this program, it should still run. Why? Because we know that it will search GAC and it will find that assembly there. So let me run that and look at this, it still runs. Why? Because our assembly is now present in the GAC. So .NET assembly resolution algorithm is very simple and straightforward. There is no complexity whatsoever, no registration of assemblies, nothing of that sort. It's very simple and straightforward. On this slide, you can find resources for ASP.NET and C# interview question. That's it for today. Thank you for listening. Have a great day.